In the last part of the session on statistical geochemistry, we'll be talking about principal component analysis and factor analysis, and these are very highly used methods, and so it's very important to get an understanding of what they do, what they are, and also what their limitations are, what assumptions are lying them, so we don't overinterpret results. So there are a number of publications. Of course, you can always look into a general publication on multivariate analysis, such as the book by Herdel, which I think is very nice. It's a fairly, let's say, it's not too overly complicated in terms of the math, and the examples are reasonably simple as well, and it's quite educational. Then there's a paper by Riemann and Phil Moser. So again, the set of authors that look a lot at geochemical data. And so there's a paper that talks about factor analysis, and particularly on the challenges with factor analysis when we're applying it into real sort of big data type of problems. I'll also mention a few examples. I just found them on the web. I think they are simple but very illustrative examples of what we're trying to do here. So everything comes then back to what we already been discussing is the geometry and the nature of data. And so when we look at data, and particularly multivariate data, then there is sort of two dimensions we have to worry about, which is one is the dimension of the variable, the other is the dimension of the amount of observations. And previously I've mentioned that there are two ways of representing that information. That's one is to look at the cloud of endpoints of variables, for example, plot height versus weight, or you could also look at individuals. So what is the height and weight for each individual, or for what height do we have a certain individual, etc. So that would be a different kind of setting. The setting that we'll be working with is the setting here on the left that is basically looking at variables and correlation between variables. On the right, we'll not be discussing that kind of operations, but you can imagine that there are methods that deal within this realm of the world. So in the course multivariate analysis and statistical geochemistry, we've talked a lot about projections. And so in projections, what we mean is that we're finding ourselves in a quite high dimensional world, and we'd like to represent that world with a smaller amount of dimensions. And so in a linear sense, we could say, well, what if we take our information? So in this case, we are in p dimensions. P is the dimension of the amount of variables you're dealing with. And we have the number of data points. These are the samples, individuals. So we'd like to project these samples onto, say, a single line. What if we just take one single line? What would be the best line, so to speak, that can represent our information without having too much loss of information? Of course, we're going to lose information by that projection because we are changing our data. But we'd like to have some kind of minimization of that. And so what we'd like to minimize is the difference between the projections that we make and the original data, and that in a least square sense. And so what is that line? Well, there's a little math around that, but let's look at this in a simple setting. Take, for example, this two-dimensional problem here where I have data, say one variable on the y-axis, another variable on the x-axis, and I observe some kind of correlation between those two variables. So you can imagine that if I take a linear line like the ones that I have here and create a projection, that means I now project orthogonally all these points onto that line, then I get a new data set, which is now univariate. And so in that univariate data set, I can calculate the variance. So this is the variance of that univariate data set as compared to, say, the total variance. And we notice that by making that projection, I have already, say, quite an amount of variance that can be explained by that projection. If I take a projection of this kind, then I will notice that my explained variance is a whole lot less. So I'm looking for the line essentially that maximizes that variance. So it turns out that that line in this particular case is simply created by the correlation coefficient and by the linear relationship that exists between those two. So the way it's being done simply is by, in this particular case, is to look at the correlation matrix, which is 2 by 2, and to create an eigenvalue decomposition of that correlation matrix. Then what we'll get is that we'll get an eigenvector that is essentially this red line, and an eigenvalue that tells me how much variance is explained along that line. And that's basically what eigenvalue decomposition provides you. So then we can start continuing doing that. If you have more than 2 dimensions, say you have n dimensions or p dimensions, then you can look at the first eigenvalue is associated. The first eigenvalue is the largest one, has a particular eigenvector. The second largest eigenvalue is another eigenvector. Of course, these two are orthogonal. And what I can then do is take these various eigenvectors and project our data onto those eigenvectors and creating thereby new variables, which we'll call factorial variables. So you notice here that we get a mapping of our data x through this vector, projecting on this vector into a new variable. So if we write that out, but knowing that our original data consists of p variables, that basically we're now associating a weight with each of these p variables. I've also a term that's used a lot in principal component analysis is the term loading. So this is basically saying that in the first factorial variable, if this loading is large, then basically that means that this part of the of our vector that this particular variable is going to be important. And that's something we need to take along in an interpretation, because that actually may have some particular meaning. Why, for example, do we see in one particular factorial variable a very large loading to a variable and a little lesser much loading, say 0, another factorial variable? Then we can start associating factorial variables with some sort of interpretations and processes that are happening in our data set, or that have created our data set. So in general, we'll get a number of principal components, eigenvalues, vectors. There are also principal component vectors, and we can start writing creating all these factorial variables as a function of the original data and the eigenvectors of the system. So this is principal component analysis. That's what it really comes down to. Looking for linear combinations of the original variables that have largest variance, and thereby being able to decompress or compress the data set into smaller parts, smaller linear combinations that are meaningful. So it requires knowing the mean and the covariance, and we have to worry a little bit of appropriate dimension reduction, but we'll see in the next couple of slides that will be determined by the eigenvalue structure that we have. We also have to worry a little bit about units of measurements, and I'll come back to that. Simply because principal component analysis, because it relies on covariance, and covariance is basically a variance, then the units matter. So you may have variables of different units, and starting to mix them may be an issue. So standardization is an option that needs to be considered, but then also may lead to different interpretations. So here's a simple example. It's an example out of the Herald book about Swiss money. And the idea that by measuring certain attributes of this kind of currency, at least in those days, one could detect genuine bills versus counterfeit bills. And so to do that, the way it was done is to take several measurements, such as the length of the bill, height of the bill, distance of frames, etc., length of diagonal. So we basically have 6 variables, and then attempting to figure out, first of all, can we use this to predict counterfeit versus not counterfeit if I have some sample data? And secondly, what of those variables are important in determining that? So which are sensitive to determining whether it's genuine versus counterfeit? So a little bit more math before we look at that. The first thing we do, of course, is to take our data and calculate a covariance matrix. So here the covariance matrix is given by sigma. We do an eigenvalue decomposition on this covariance matrix, and then we calculate our factor variables by transformation. So here we notice that this is the transformation of the factor variables of the original data into factor variables. So at least theoretically, if you say this is just based on theory, so no sampling, we can then have the following properties: is that the mean of this is 0, the variance is related to the eigenvalues, their covariances are 0, so they are orthogonal, and their variances are ranked according to the various eigenvalues. Of course, in reality, we need to estimate all these properties from limited data. So it also means that that the principal components or factors that we get are only estimates of the actual factors in the entire population. We also notice bijectivity. That means that that you can go from x to y in this way, but you can also go easily from y to x by just multiplying everything on the other side. So, so that's a very important property of principal component analysis, is that you can go from data into low dimensional space and then back to the data space. So you may then, of course, lose information depending on how many of these eigenvalues you retain in such calculation. So if you apply that to the Swiss money example, so now we're estimating all these terms, particular covariance matrix, then we can plot the various principal component scores. This is now these factor variables into say a lower dimensional plot. So the first of all thing that we can look at is what is the contribution of each eigenvalue to the total variance. Actually, this is just the eigenvalue itself. So we see that the first eigenvalue is a high value, and so remember the eigenvalue was related to the variance of these observations. So the second one has already less variance and less variance. So at some point we can chop off this whole series and deal just with a limited amount. And it seems quite clear in this particular case that if we chop it off at 3, that intrinsically in this data set there's only really 3 variables. The other thing that we notice is that when you plot first versus second principal component, is that you end up having 2 populations. And so that's in a way that we can start using principal component analysis to regress and classify the whole problem based on just 2 variables instead of 6 variables. We don't see that correlation necessarily in other principal component plots, but that is somewhat expected, of course. So how many of those variables do we look at? Well, that's here at the bottom explained here, is that we just calculate what I call the cumulative proportion of variance. So what we do is we look at the eigenvalue total variance, and we say if the total variance is, I don't know what the total variance here is, say it's 3 or 4, then the proportion of that first eigenvalue is 0.67. And so if I sum up that total, I get this total, this is amount, this total amount here, divide that then up. So if I take now the first 2, that means I take 2.9 plus 0.9. That's going to be about 4, and that will explain then 88% of variance. If I add more, you see that incrementally I'm adding less and less amount of variance. If I use all of the eigenvalues, then obviously that will get the total amount of variance. This also means that in eigenvalue decomposition, you can always perfectly reconstruct your data by taking all of the eigenvalues. And that's something that where differs from factor analysis, where the goal is not to do that. It's not just to maintain total variance of variables. So then we also need to look at loadings. Loadings, remember, these are our original variables. These are principal component factor variables, and we notice that for the first factor variable, we get a low x1, low x2, low x3, and then we notice a big load here, lowish, and then again a high but negative. So you could say that the first principal component variable explains basically the difference between x4 and x6 in some sense. In Y2, it's a little bit more complicated. We have here now at the end we have 3. So this also shows why we get 93% of variance, is that most of the loading goes onto 3 of these components here, and this is only very little. And so that explains now that the second one is somehow is a curvature. Let's say it's a minus this plus that minus that, and so that allows you to interpret that component as in that sense. So here's an interesting example or illustrative example of how principal component analysis can be applied in geochemistry. So the paper is a paper I mentioned in the beginning, and so if you'd like to read more about the details, feel free to do so. The point I will illustrate here with this data set is how to interpret loadings, and also start to introduce you a little bit to the notion of spatial distributions and the fact that our data is spatially distributed, not just multivariate, and how factor analysis, principal component analysis actually can contribute to the interpolation of say highly multivariate, complex multivariate data, and that's something we'll do when we talk about geostatistics later in the course. So in this case, the authors were, it's a similar example to say that we've been talking about a lot in soil geochemistry, is people go out, take samples, do very sophisticated analysis. There's a large amount of samples in this case, there's a large amount of elements involved. But in the end, that's what we get. We get samples distributed over an area. And so they again would like to know, here we have a glaciation, we have bedrocks. So they'd like to understand what are the geochemical processes that created these various soils or tills in their particular case, because we're dealing with glaciation. And so that was the purpose of that study. The thing I want to point out with this study is to start interpreting loadings. And that is done in this particular case. So I kind of like this plot, the way the authors did it in this case. There are many ways of displaying loadings, and so the way it was done here is by sorting them from highly positive to highly negative, although it's not very highly negative, but positive to negative. And so what you then notice is that indeed what we have is a bunch of things that are positive and a bunch of things that are negative, and possibly a bunch of things that are very small. And that's what you see in the first principal component here. And so one way of looking at this, as I always think, is by means of filtering, is that your samples, now you have samples, you have actual, remember the way it works is that now imagine you have an actual sample that you take from your area, say this sample here. The principal component, the way this is calculated, or the factor is calculated, is by taking that sample and multiply it by these loadings, and that gives you the first principal component. So that's the new variable you create. So you can notice that what is basically, because you're doing sum and multiplications, is that you're multiplying a bunch of these with high values, a bunch of these with low values, and that can be interpreted as a gradient, for example, right? A gradient means that you take something and you subtract something else, looking at a difference. So the first principal component, we're looking at the difference of these variables and these variables. And so that may be indicative of a certain process, or may be related to some other type of observation. So in this case, most of them are positive, and so you could say that basically the second principal component is some kind of a weighted average and they're all positive. You could say this is negligible. Then you can plot those scores onto a map, and then you get, of course, the high scores. So these are basically all the samples where you see indeed a difference between these guys and these guys over here. So that's indicative of that difference. So that's what that would be interpreted. Here we see blue would mean, I guess, low difference. I don't know what the color bar here is exactly, but that you can imagine that the color bar is indicative of how different these elements are from these elements at those samples. You also notice that you get clearly spatial correlation. There are areas that are red and areas that are blue, and we can imagine now interpolating these factors, and then we can, once we've done that interpolation, we can go back and reconstruct the original samples. So it suggests a method also of a spatial interpolation and reconstruction, and that will be very useful and something we will revisit later on in the course. So now we've covered principal component analysis, we can move on to factor analysis. So in factor analysis, the real goal is to use your data and to start to understand whether there are any process or causal influences that are producing this kind of data. And so these unobserved causes or influences are called factors or latent factors. So these are not observed, and that's of course an issue. And so can we discover them? So the idea is that we take this highly dimensional data set and try to find a limited amount of factors that that can explain that variation. So how to discover them? Are they unique? Probably not. Would you say, well, is this not PCA? PCA is different from factor analysis. So in PCA, we look at a total variation of the data. So we always try to replicate total variation. That's why I look at total variance. And so in PCA, we're looking at this bijective operation of maintaining total variance. In factor analysis, we're going a little bit further. We're trying to explain variation by a very particular model. And so that requires certain model assumptions that will need to be met that are not necessary in PCA. So here's the theory as a whole. And so, as I said, we have our data set. So this is our variable we're trying to model, which is our multivariate variable. What we try to do is to say there are some factors that are smaller, so p k is less than p here, that can explain that, and there are some other noise parameters, let's say, that that are not common. They are only specific to each variable. So we'll have something in the model that's our factors. Linear combination of factors explain the data, and then there's some noise term in the mean term. So just like in PCA, we'll be working with factors, of course, that that are orthogonal, and noise terms that are orthogonal and are orthogonal to each other. So this is just a mathematical model. So I thought perhaps it would be better to explain it with a simple low-dimensional example. So here, this example I borrowed from Peter Trifle's book, which was a business case book. A lot of these factor analyses are used, of course, in business, marketing, psychology, healthcare, etc. And so here we're looking at student grades. And so we have business school students, and there's 3 grades that we're looking at. One is finance, other is marketing, and the other is policy. So the 3 variables we're looking at is finance grades, market grades, policy grades, and then we have a number of samples, which are the students. And so what we expect here, or what we're thinking, and this is sort of a setup of the problem, is that we are thinking that there are 2 underlying factors in here that determine that, and it sort of makes sense of this example, and that's why the example is set up like that. In reality, you would, of course, you can only sort of hint towards the particular factors, but here we know that quantitative abilities will do well in finance courses, which require a lot of some of these finance courses may be mathematically oriented, while verbal ability are more important in the marketing and policy courses. That requires a different skill in students. And so the question is, can we explain the variation we see in these grades by means of these underlying factors? So in this particular simple example, we assume we know the underlying factors to some reasonable certainty. So if you now come back to that factor model, which was written in matrix notation, and we can write it out here. Now the x is replaced by a y, but everything else is the same. So we notice a number of things. Is there's a constant here at the front, so that's our mean. Then we have factors that are the 2 factors. Say we think there are 2 factors, not 3, not 1. By my pointer, we think that we have 2 factors, factor 1 and 2, and then we have some error terms. So that is just say there's specific variation, some noise variation that's specific to this model and not specific to any other model. So these noise terms, they are orthogonal, factors are orthogonal. So in this particular case, we could say that there's a factor that has to do with quantitative, where the quantitative factor will have a big influence on score 1. So what we will probably expect is this beta 1 to be positive, while the second factor, the verbal ability will basically be low, and so the beta score for that will be low. And similarly, if we go in the opposite sense, namely we look at the more verbal oriented course versus quantitative course. So this is basically what we're trying to model, is to say, what are these loadings? And in the end, we'd like to make tables like this, is where we say, these are the variables, these are the loading, and we can start to understand what these factors actually mean and what they would influence. So that is the theoretical factor model. And so what we'll try to do is to write down if this was the true model, so the model that would generate our information. So if our y was indeed a linear combination of two factors and some random error, what will be then the corresponding covariance matrix of these y's? And so the covariance matrix of the y's would then, of course, depend on the beta values, factors that we have, the definitions that we make. And if you then look at the variance of y, you can calculate very easily that the variance of y is simply the square, the variance of f here, the square of beta, the variance of f, and no covariance term, simply because the factors themselves are independent, so that covariance terms is no longer present. We also said in the beginning that the factor variance is, we take that to be 1. And so that means that the variance of y, of any y, can be written based on these square betas and sigma. So we say here that if we now look at this a little bit more close, is that this noise term is just specific to that particular factor. So this is the noise on that particular variable. And the first part is the commonality part, is that part that's actually explained by the factors, the common factors in the data set. So it's the commonality of the factor that produces the kind of variability we see in this data. So typically we call this sum here the commonality, and that's something that we often display in addition to other information. What about the covariance? Well, we can also do the covariance calculation. Again, covariances come out that variances are dropping out. Variances of things are unity, and so, or the variances, sorry, of these are independent. Of these two, of the errors of these two are independent, so they drop out, and we end up with this term. So we can now arrange all this into this single table here. So this is now the table that says that if the factor model is the true producing model for my information, then I would expect this to be my covariance matrix. So logically, then you could say, well, now I have a theoretical model, this table here, and I can calculate, of course, from my, even though I don't observe the factors, I can still calculate from the observations that I have the empirical covariance matrix. And the empirical covariance matrix are these empirical entries here. These are the variances, and these are the covariances empirically calculated. And for example, for this particular case, for the student case, we notice that this is the covariance matrix. So we notice a high variance in the first factor, a lesser variance, first variable, lesser variance in the second variables, and we see also no correlation. So if I calculate the correlation matrix, I find a high correlation between y2 and y3. So of course that is due to the underlying skill that generates this, namely the verbal skill that generates this kind of data. So the question now is, okay, do we have some information here? We have some information in there. Can I estimate the betas? Well, in mathematics, before we're doing anything, we have to think about uniqueness of the solution. Is there something that can be unique? And the answer is no in this particular case. So let's investigate that a little bit. For example, imagine I have sort of created two fake factor models here. One fake factor model A and another fake factor model B. And the particular loadings of these factors are given over here. So these are the loadings given to factor 1 and 2, for 1, etc., etc. So if I look at these two factor models and I look at them in terms of the covariance, so I plug this now into my covariance matrix and I calculate covariance, I find that the covariance matrix for these two factor models is exactly the same. And so while this factor model is very different, for example, here I notice the factor is 0. So y1 is only a function of f1, and here it's a function of f1 and f2. So, and that seems like a big problem, right? Because if I'm going to interpret this factor model as something to do with underlying causes and influences, then my calculations can give me, it seems like, a large variety of possible factor models. So that means basically that we need additional constraints. So where would these constraints come from? Well, in order to understand that a little bit better, is to look at what happens, why these two give you the same covariance matrix, and that has to do with rotation invariance. So remember in the previous slide, I had a number of loadings. I had 3 variables, I had 2 loadings. So if I plot these loadings into a Cartesian axis system, then I noticed that these loadings here, 0.5, 0.33, they lie on this 45-degree line, and this other loading lied also on the orthogonal line here. So that also means that what I can do is I can take this axis system and turn it 45 degree, or I could say I take this guy, turn it 45 degree, and create a new axis system. I have not changed any information because it still have orthogonality and etc. But of course now in this new axis system projected on here, I have now essentially a new set of loadings. So this shows that rotation is an interesting additional component that can be used in creating certain types of loadings into your system, and that's what we'll be discussing next. So this also means now that a standard factor analysis will consist of 2 steps. The first one will be determining some kind of a factor model, meaning determining the loadings. Then, of course, knowing that those loadings are not unique, we'll have to then do a second step, which is rotating the axis system to impose some additional interesting properties. The problem perhaps in the second step is that it may be very tempting to rotate the axis system to a position where you already have a preconceived interpretation of what the system should look like. And so we'll come back at the end to this issue of the various warnings that we need to have about factor analysis and how it can be misused. The whole point here is not to use the data to prove already some pre-existing point. The idea is to discover in the data some things we hadn't perhaps seen before. So there are many methods, again, for both operations. I'll just focus on the most common one. The first one is called the principal component method for step 1. So here, what we're going to do is we're going to ignore the covariance terms. So I'm only going to look at the observed variances. And so the observed variances are represented by these observed commonalities. So this is then the total variance, and this is the total commonality. And so what we'd like to see is to minimize the difference between those two and find then loadings that can reflect that. So here's an example of doing that. So you have here the variable, the observed variances. So remember, finance was at the largest variance, the total variance. And here we now see the estimated beta coefficients. So the B is the estimated beta, just to make sure a difference between, make a difference between beta as a theoretical parameter and B as an estimate. And so what we notice is that for finance, we get it scores high on factor 1, scores low on factor 2, and for the others, the exact opposite. They score low on factor 1 and score high on factor 2. So we can also look at the commonality and then at the percent explained. So we notice here that this commonality explains a lot of this variance, and we get this high percentage. So in this case, because it's such a nice obvious case, everything works out quite nice, and there are very little errors remaining, uncertainties or remaining errors in the system. One thing we have to worry about in both PCA and factor analysis is the sensitivity to units, simply because of the fact that my variable y that I have depends on the scale. So if I work in pounds or kilograms or meters or kilometers or feet, then that has an impact. And so what can be if units dramatic differently, what can be very useful is to standardize things. But then we have to also worry that everything, the interpretation is going to change again. And so what we have here is this is now the same result, but now repeated for the standardized variables. And so now we notice that finance is now dependent on factor 2, and factor 1 is giving more weight to marketing and policy. We also notice, of course, that we get much smaller numbers than before. because of the standardization. So now we come to the particular rotation method. So this is a very known and common method. Actually, it's very known and common in many applications of principal component and analysis and factor analysis, called the varimax method. The varimax method, we're going to rotate the axis system such that the rotated loadings are maximizing the variance of the squared loading of each factor. So we're looking at maximization of variance. So the time may be a little theoretical, but what that basically means is that we want to make some loadings as large as possible and some as small as possible. We want to get as much differentiation as we can, because differentiation and loading, what we don't want is we have a lot of loadings that are very similar. We want to have more differentiation, and that differentiation will allow us to have a better interpretation in terms of the common factors and influences, and also to minimize the amount of variables that are needing to be used to determine these factors. So here we have the varimax rotation and on the standardized variables. What you notice here is that there's not a whole lot of difference with the previous table. The only thing that we notice is that these numbers have gotten even closer to 0, and these haven't gotten even closer to 1. This number has certainly decreased a lot. And so, but in this particular simple example, the rotation doesn't do a whole lot. So how many fixed factors K should we take? Well, there's no really a single rule that you can apply. Say, here's a rule and apply it. First of all, we could just have insight a priori about the amount of factors that are there. We just don't know what they are. So that's often probably more important than anything else. We can also look at the eigenvalue decomposition and the structure of that. So we can take those eigenvalues and look and explain variance. That will be this second part here, this here. Or we can look at the scree plot, as the plot I showed you before, and take where you plot that cumulative variance against the cutoff and take it at some elbow point. So there are many ways of looking at the same problem. In the end, it's going to be a decision that has to probably be based more on insight of the problem rather than on some statistical measure. So let's do a very simple example here of factor analysis, and that will be in the assessment of groundwater quality, and particularly its relation to Blackfoot disease, which is a disease caused by arsenic into the groundwater system, gets into the groundwater system. So what's the issue? As I mentioned, we're looking here at explaining a particular disease, and so in often these countries, same in Bangladesh, and there's a lot of overpumping of the groundwater system, and so that leads to either seawater intrusion, which is always not good for agriculture, and secondly, it reduces excess dissolved oxygen, which often is related to the release of arsenic into the system. That could also be to the overpumping is that there is more higher influence of surface pollutants. For example, agriculture will then draw some of that into the subsurface. So the questions here raised were, can we delineate zones of seawater intrusion, arsenic pollution, and can we possibly identify some of the main hydrochemical causes of both? So here's the data. So it's in Taiwan, as I mentioned, in Yunlin County. And we have a number of samples. In fact, we have 28 samples of water quality in the groundwater. So this is our data matrix, and so we measure a number of things, some cations, ions, electrical conductivity, alkalinity, total dissolved solids, total organic content, TH was total hardness of the water sample. So we do our factor analysis now. So we do standardization, we do the principal component model, and we do a varimax rotation. And so at the first two factors, we already get about 80% of total variance. And so what we notice is immediately some interesting observations. So in the first two factors, the first factor is about 56% of variance, the second has about 21% of variance. we notice that we have a big loading on electrical conductivity, low on alkalinity, high on TDS, chlorine, you see here sodium, potassium, low on arsenic, etc. So this factor model obviously is related to the seawater salinization issue. So that's kind of nice that that pops up into a single factor. The second one we notice immediately is highly correlated, or to arsenic we have a big loading here, and it's nice we get a small loading here. That means that it's somewhat independent of that, but it is also associated with other things. So not just that we're looking at arsenic, you can also look, for example, it seems that total organic content is important, alkalinity of the water is important, etc. So now that we have this factor structure, what we can do now is take each of the samples and map that into the factor space. That basically means is that filter that I talked about previously is have a sample, run it through the loadings, and calculate the score of each sample for the two factor structures. So now we have two factors, and we have again 28 samples. And so of course these samples come from something in space. So now we can plot these various factor scores onto the map, original map, and do some spatial interpolation. And so based on that, instead of interpolating every single variable, which could be another option, but that's difficult, particularly because those variables are correlated, we can now interpolate those variables independently. Something we will return to when we talk about geostatistics and interpolating multiple variables. So what we notice here is indeed that factor 2, which was to do with arsenic pollution, has a high score over here. And so that's a zone that can be contoured as highly polluted, while water intrusion is more prevalent in this area and less prevalent in the area of the saltwater intrusion. Okay, so what if you go to a bigger data sets? Because the previous data set was relatively small. I think we had possibly 10 to 15 variables and 28 samples. But in this COLA data set, we're looking at over 50 elements, and so hundreds and hundreds of samples that are available. And so it becomes a whole lot more challenging to do that. Why does it become a whole lot more challenging? Well, first of all, we have mixes of things. So often major and minor oxides, but also we have trace elements. So we have to account for this difference in amount of variation. So standardization is a big issue here. For most of the cases for PCA and factor analysis, we do assume some form of normality, so for things to become easily interpretable, and that's often not the case. And so that's something we have to worry about. We also have to worry about the compositional nature of the data. So closure is not treated later in the course, it's already treated. We'll have to, instead of working directly on the elements, we'll have to probably work on the ILR or CLR or ALR ratios. And so that's something to take into account. As I mentioned before, outliers are a big problem with any kind of covariance-based methods, and so removing them from the analysis in terms of calculating the covariance, at least, is going to be important. There may be multiple populations that exist, etc., and data may have spatial correlation, which essentially is also something that we assume is not occurring, because spatial correlation means the samples are no longer identically and independently distributed. In any case, we can run factor analysis. This is done in that Riemann paper. And here we see they chose about 6 factors, and we see here the loadings of the various elements. And so now it becomes a little hard to understand and hard to look at. So what is often done is to make this kind of plot. So in this kind of plot, we have 2 axes. The first axis is the y-axis here is the loading that is given to an element, and the x-axis is the percentage of variance explained by each factor. So for example, the first factor has 39% of variance, and it seems to have high loadings in all these elements. Second factor has and adds to that 14% of variance and seems to have high loading on these factors and a few negative loading. And this is actually quite good news. For example, here we see these are all rare earth elements. So that means that the first factor has something to do with a process that increases or decreases the amount of rare earth elements into the system, or there's at least a variation of that. So in this particular case, that can actually be associated by, we can look at that in space. So this is the same COLA data set, and we're looking at those samples over here. And it turns out that all those samples with that high first factor variable lie over here, the sum over here and here, but there's definitely a concentration of it there. And so this was explained as soils that are overlying alkaline intrusion and have related to that complex that was present in that location. So some final warning, factor analysis is great, but there's a lot of things that can go wrong. As I mentioned before, it should not be used to prove anything. It just be used to enhance scientific understanding, because it's easy to say we have some data, we see correlation, therefore we have causation. And so this is the same correlation causation problem. So factor analysis should be used to support understanding and possibly discover something that was not discovered before. Then of course, if you were to support something, then there's a danger that you play around with the whole system, and there's a good way to play around. There are many methods of doing the loadings, determining loadings, and methods of rotating. So somebody that's smart can go play around with things until they find something that's reasonably within the line of what they'd like to see. And so that's something, once you start tuning things, I think then things are going wrong. There are many issues that we have to verify. As I mentioned, how you estimate the loadings, how you rotate, how many factors that you use, potentially how many variables you retain, what kind of outlier detection method you use. It's always good to verify robustness. It means like what if kind of scenarios to test all these things out.